So we'll start today with problems on LCOE and de-risking. To start with, we have the following. Consider a 429 megawatt power plant of 20-year lifetime operating based on an advanced natural gas combined cycle. The plant is characterized by a capacity factor of 90%, a capital cost of $1,104 per kilowatt, a fixed annual cost of $10 per kilowatt, and a variable operating cost of $2 per megawatt hour. Natural gas is used with a heat rate of 6,300 BTU per kilowatt hour and is sold at $5 per million BTU. The discount rate is 10%. We want to calculate the life cycle cost of electricity of the power plant. Okay? To start with, we know that LCOE is given by the following formula. So LCOE. Yes. We should consider if you want the life cycle cost first. Okay? So you already know how to calculate the life cycle cost. What is just new here is that we divide by the life, yes, by the operational lifetime. Okay? To be able to have a normalized value that will allow us to compare different strategies, especially if you have different lifetimes, different resources. If you have a if you want a plan through the years that is very different, to be able to compare different strategies, we need a normalized factor. Okay, because if you have a very different lifetime, you cannot just maybe compare just the LCC. Okay, you need to have a normalized factor, which is LCC over the lifetime discounted output. So we will both discount all costs to present, and also we need to do the same for the outcome. Okay? Now, to start with, they said that we need to see how to use the information given. So first, we have a 429 megawatt power plant. The lifetime N, so this is the power P. P equals 429 megawatt. We have the lifetime N. And of course, when we say we want to calculate the life cycle cost, we need to consider for the whole lifetime. Operating based on an advanced natural gas combined cycle. The plant is characterized by a capacity factor of 90%. How we use the capacity factor here? Not only this, look, you know, you need to consider the total energy in 1 year. Yes, so what? Yes, very good. So we should first, this power, we should be calculated now. We should have energy. To calculate the energy, we multiply by time. Okay, so the energy output, if you want, from this power plant, exactly, 90%, the maximum possible output. So 90%, so 0.9 times maximum output. And the maximum output is if the power plant will operate continuously with non-stop. Okay, so the maximum output can be calculated as 429 times the total. If you want to have it in megawatt hour, you should multiply by the total number of hours per year. So number of hours per year.
365 times.
Yes. 429, of course.
365 times 24.
Yes. So the number of hours per year is 365 times 24. Okay. In this way, we'll get what is the output of this plant in megawatt hour. Okay. Now, they gave us a capital cost of $1,104 per kilowatt, a fixed annual cost of $10 per kilowatt, and a variable operating cost of $2 per megawatt hour. In addition to these costs, we need natural gas. So we need to know how much we are consuming. They said that natural gas has a heat rate of 6,300 BTU per kilowatt hour. So we already calculated the number of megawatt hour needed, okay, produced. So we multiply by 10 to the power 3 to get the number of kilowatt hour, okay? Then when you multiply by the heat rate, so when you multiply by the heat rate, exactly, we get what is the amount, okay? So we find the amount of natural gas needed, okay? And then we can, after we find the number of BTU, we have the price in dollar per million BTU, okay? So we just have, when you get this number in BTU, you should divide by 10 to the power 6 to get the number in million BTU, okay? And then you multiply by 5 in order to find the total cost, okay, of a BTU needed. So we need to do the following. We'll go again through the numbers. So all we have to do is to multiply first. Just we should pay attention for units, okay? Number of megawatt hour, we multiply by 10 to the power 3 to get the number of kilowatt hour. Then, since we know what is the heat rate per kilowatt hour, we can determine by multiplying by this number, we can determine the number of BTU required. And since the unit here is given per million BTU, we divide the number we got by 10 to the power 6, and then we multiply by 5. We get for each year what is the cost of natural gas used, okay? Now, they gave us the discount rate because whenever we calculate the LCC and the outcome, both should be discounted. And we should calculate everything back to its value at present, okay? So now we are ready to do our calculation, okay? So let us organize the information. So first, we need to determine the life cycle cost. For life cycle cost, we need to consider the initial cost. And for the annual cost, we have to consider 3 factors. They gave us first a fixed annual cost per kilowatt. So of course, we just have to multiply this by the number of kilowatt. They gave us also another operating cost that is given per megawatt hour. So we just have to multiply this cost by the number of megawatt hour. And in addition to this, we have the cost of natural gas that we should buy for each year, the annual cost, and we have seen how to calculate, okay? Yes?
Just for the fixed annual cost, $10 per kilowatt, why did you use the maximum power?
No, we'll not use the maximum power. We'll use, of course, we multiply by the, of course, yes. Okay, so whenever, when they gave us, if you want, here, look, when they give you the capital cost per kilowatt, it is for the characteristic, if you want, of the plant. Okay, yes. It's not, whenever you want to calculate the output, you consider the capacity factor. But when I tell you you have a plant of 429 megawatts, this is the power of the plant, okay? So when you perform your calculation and you want to find this kilowatt is from the characteristic of the power plant. But when you want to find the output of your power plant in megawatt hour, then you should consider the capacity factor.
The capacity factor is only for the energy.
Yes, only for the energy because it's related to the time of operation. The power will not change. So if you operated 5 minutes or 1 hour or for the whole time, the power is the same. What is different is the time of operation. So whenever you need to determine the output, you need to consider the capacity factor. And whenever you need to, whenever you just have it per kilowatt, you go back to the rated power of your power plant. Okay, so that's why when we calculated the initial cost, the initial cost is defined per kilowatt of power of the power plant. So we just have to multiply by the number of kilowatt, which is 429 times 10 to the power 3. So this is the number of power of our power plant. Now, why we divided by 10 to the power 6? Because we gave all numbers in $1 million because the numbers are huge. Okay. So to simplify here, we just divided by 10 to the power 6 to convert from dollar to $1 million. Okay. So this is for computation of the initial cost. And of course, the initial cost is, if they don't say anything in general, it's at year 0. Sometimes in the descriptions, they tell you you have, let's say, a grant, but this grant is divided over years. Then you can consider for year 1, 2, 3, you discount values. But when they just say initial cost without any other information, then you consider that it's at year 0. Okay. Now, as we said, the annual cost is divided according to the given into 3 parts. You have the fixed annual cost, you have the variable annual operating cost per year, and you have the natural gas cost. And we just have to pay attention for units because units can vary depending on the given. So they told us that for the fixed annual cost, the value is given in dollars per kilowatt. So we just have to multiply by the number of kilowatt. And as we said, we take here the power of the power plant, which is 429. And since the value is in kilowatt, we multiply this number by 10 to the power 3. So we have, we just need to do the number, which is 10 times 429 times 10 to the power 3. And we divide by 10 to the power 6 because we need to convert from dollar to $1 million. Okay. And finally, for the variable operating cost, this one is defined per megawatt hour. So here we use the capacity factor. We already did it. You do it once and then you use the result. So to get the number of megawatt hour, as we mentioned, you use the power of your power plant. You multiply by the capacity factor and by the number of hours per year. Okay. So now when we add all of these, we'll get the total number, the total cost, okay, related to these 3 parameters. Now, when we consider the natural gas cost, as we said, we just have to consider the number of kilowatt hour times the heat rate, which is in BTU per kilowatt hour, times the price in dollars per BTU. And since they gave us the price per million BTU, we just have to say the price in dollar per BTU is just 5 over 10 to the power 6. Okay. So now we just have to replace and we get then the total annual cost equal to $117.5949 million. Okay. Next step, now we are ready to perform our calculation. Okay. So this is the formula of LCOE, and you are responsible of this formula, of knowing this formula. Okay. So LCOE is the levelized cost of electricity, and the unit will be currency, monetary unit, which can be dollars, euros, depending on the problem, per megawatt hour or per kilowatt hour, etc. And they will tell you which unit to use. If not, you can use whatever you want. Okay. In the numerator, as we said, we have the life cycle cost. So we have the initial investment plus summation from year 1 to n of the annual total costs that we already computed together from the given over 1 plus a to the power t, where I represents the discount rate considered. Okay. And you already know the discount rate can be calculated as, in case you have a private investment, you can consider the WACC calculation. Okay, and in case you are doing economic analysis, you take the rate that is imposed as a public rate. okay? Now, for the denominator, we need to consider the lifetime discounted output, okay? So for each year, I need to consider the number of megawatt hour over, so I do summation of annual output in megawatt hour per year over 1 plus I to the power t. In this problem, the calculation is relatively simple because we don't have variation with time. So for all years, we have the same annual cost and we have the same output. But in case you have variation, you already know how to deal with it, okay? And for example, let's say the production in year 1 is different than year 2, different than year 3, and it continues for the remaining years. Yes, you just decompose the summation. And you take the different terms plus summation, for example, from 3 to year n of the constant part, okay? So now, the numerator of the LCOE is just the life cycle cost of the project, as we said. So to calculate it, we need just to apply the simple formula, which is that LCC is summation from year 0 to year n of the annual cost, okay, over 1 plus a to the power I. And since here the parameters are really simple, we can just do manual calculation. So we can consider first for the investment, of course, no need to, it's at year 0, so it's not discounted. So we already evaluated the value in $1 million for the initial investment. We put it as it is. Now we add summation from year 1 to n here is equal to 20 of, since the annual cost is constant, we can take it outside of the summation, which is 117.5949 times summation of 1 over, the discount rate is equal to 0.1, so 1.1 to the power I, okay? And since this is a geometric series of known expansion, we can just replace it by 1.1 to the power 20 minus 1 over 0.1 times 1.1 to the power 20, okay? So, and we get then the life cycle cost. Now, for the denominator, we have to consider the total lifetime discounted output. So also here, we have determined this represents the number of megawatt hour per year. And the inputs to calculate this number are the power plant power, the capacity, and the capacity factor. Okay.
Doctor,
Yes, Rida.
only power has discounted output. Why discounted? Power.
Okay. The power, it's the output is discounted because, as we know, Rida, with time, okay, all costs and incomes are discounted. So when you perform, for example, the net present value analysis, you discount incomes and you discount costs. Okay? So here it's the same. You should discount costs and you should discount also your output. But now instead of having your output in monetary terms, you have it in megawatt hour. Okay?
بس هو اللي مش مرتبط بالLCC.
لا, look, the LCC is considering only costs. But here, the production, if you want, is an indication of what here? It's an indication of the output, of the revenue of this power plant. Okay? Yani, the LCOE, if you want, is a way to normalize your results. Instead of just calculating the net present value, which is I0 plus summation of Ri minus Ci over 1 plus a to the power I, you are considering the ratio of cost to the income, and the income here is not in monetary term, is in effectiveness term. So here the effectiveness term is the number of megawatt hour produced. You can have, for example, other factors. If you need to consider environmental factors, let's say, you can consider in the denominator the number of CO2 reduction in CO2 emissions, for example. Okay?
Clear.
And always you need, since you are computing, you are discounting your costs, you should also discount your outcome, or you should discount any effectiveness measures that you are considering. Okay?
Okay.
So now, whenever we replace by numbers, we can get that the lifetime outcome is 28.79488 times 10 to the power 6 megawatt hour. And just now, when you divide the LCC by the lifetime discounted output, you will get for your LCOE $51.2163 per megawatt hour. Okay, so it's good to know the range of LCOE to know if what you got is reasonable or not. Okay, and this method can be used to compare, as we said, different measures of production of electricity. Okay, any question on this problem?
Capacity value percentage is
Yes.
difference between the type of fuel is used or type of the solar.
Yes, of course. The capacity mainly depends first on the type of renewable. If it's a renewable energy project,
Much lower.
yes, it will be much lower. In general, nuclear power plants relying on fossil fuels will have very high capacity factors because of the availability. You have fossil fuel, whenever you need it, you can use whatever the quantities that you want. While for renewable energy, it depends a lot on the climate and on the season. So,
depends كمان على الطاقة الموجود.
Of course.
The amount of losses in the conversion.
Of course, yes. But mainly, whenever you have a power plant that can operate, when I give you the power already take into consideration the losses you are talking about. Whenever I tell you this power plant is giving you this power, already I consider this is the output, this is the electrical power. Okay? I already considered conversion, efficiencies, losses, etc. Because this is related to electricity. Okay? But whenever I talk about a capacity factor, this means this power plant can operate the whole time. Okay? Even when we talk about, let's say, nuclear power plant or power plant relying on fossil fuels, the capacity factor is high, but you should consider, of course, if you consider what is the efficiency of the thermal cycle, it's of course below 90%. If it's 40 and 50%, it's very good. But then you are talking about conversion from thermal to electrical power. It's different. The capacity factor is related to the fact if I can operate continuously or not. If I can supply the needs 24/24 or not. This is the difference. Okay? So here, this 429 is already the electrical output. And it will consider, of course, depending on the cycle, it will consider the thermal efficiency, the combustion efficiency, which are not 90%, of course. Okay, so this number is after considering all other efficiencies. If I want to start from zero, if you want, here I directly gave you the output power. Okay, so this represent, if you want, the output electrical power. Okay, now if I want to complicate the problems more, what can I give you? I just give you, for example, I tell you the thermal efficiency of this power plant is, for example, 40%. Okay, the generator efficiency, let's say, is 90%, because whenever you need an alternator in order to convert from mechanical work of rotation into electrical. So you have losses. I can give you the combustion efficiency, for example, is equal to 95%. Okay, and I give you, for example, what is the amount of fuel that is burnt. So I am burning per year this amount of fuel, which has a certain heating value. Okay, so if let's say, for each type of fuel, you have what we call the heating value. and the heating value is in kilojoule, let's say, per kilogram. Okay, exactly. So you have the heating value, and you have, let's say, the number of kilojoule per second that I'm burning. Okay, so if I multiply, when I consider this and I multiply, I can find number of kilograms, I'm burning per second. When I multiply this, I can get what is the total, the maximum. This is the maximum power. This is the input. So to find the input, then I have to multiply the number of kilogram per second that is burned by the heating value of my natural gas or fuel, etc. So I get my input power, okay? And once I get my input power, I should multiply it by what? By the overall efficiency. I multiply it by the overall efficiency, which is the product of the combustion efficiency times the generator efficiency times the thermal efficiency. Then I will have the electrical power output. And I use this one with the capacity factor to know what is the number of megawatt hour produced by my power.
The 90%.
No, I mean this number, this input is thermal. It's your thermal input, okay? When you multiply it by the overall efficiency, which is the thermal efficiency times the combustion efficiency times the generator efficiency, you get what the output, the electrical output. So this represents, if you want, what is given directly for you here, which is 429 megawatt. This is the electrical output power of my plant, okay? And then using the capacity factor, you determine the number of megawatt hour produced per year. Yes?
Capacity factor is always given. We don't have to find.
It can be, you can change the problem inputs in a way to ask for it. Why not? It can be an unknown, but I should give you then another information. Yani if I give you the number of megawatt hour and I give you the power, the electrical power output, you can deduce the capacity factor. Okay. Other question on this? Okay. So let us do now another type of problems on de-risk. Okay. So in general, what is the idea of de-risking? Who can summarize to me? What is the idea of de-risking a project? Okay, any project presents risks, especially renewable energy projects, because we need to put a very high investment at the beginning. So we need to do several strategies to make the project more attractive, okay? And as we said, the de-risking strategies can be of several sources. You can have policy, if you can impose some policies, okay? For example, you impose taxes on non-renewable energies. You facilitate loans for projects relying on renewable energy, okay? You can, for example, also, can you suggest any strategy? We can give incentives, okay, for any investor that will invest in renewable energy, etc. So we have several categories of de-risking: environmental, social, okay, political. We can impose these de-risking measures in order to make the project more attractive. And always we have also, we discussed last time, if you remember, short-term measures, medium-term measure, and long-term measure. And the final purpose at the end is what? Is to make renewable energy projects competitive with normal one, conventional one, using fossil fuels or natural gases, etc. Okay? And we have a very good experience with PV systems. So if you take the experience of PV systems, if you go back 20 years, you need to impose a lot, you need to do a lot of strategies, incentives, facilitations for people to use PV. But now, without any incentive, people are using PV because of all research and developments that were done. Of course, for example, government also can invest in research, okay? They can invest in research to make this type more efficient with a smaller cost to make it more economically viable. And this happened with PV. We worked in parallel with policy strategy, with research and development, okay, to work on efficiency and cost at the same time. And we have seen a very fast growth of this technology, okay? So in general, we need first to study, if you want, what are the barriers facing this type of projects. So we need to understand the risks, and then we develop several categories to reduce risks: social, environmental, political, etc. Okay? Now, how we do the calculation? Let us consider, for example, the following given. So I just need to determine, as we said, I define some de-risking strategies. So depending on my problem, I can select the most important strategies. Okay, so as usual, we can do research to see similar problems. What are the most important factors that can reduce risks? Okay, and then I consider, for example, the most important, let's say, 4 strategies. So number 1, number 2, 3, and 4. Okay, now, what is the calculation technique? So you are already familiar with statistics. Always we do statistics to see the effect of each factor, okay? And in general, one of the most used methods is the following one. We have 2 important factors: the probability that this de-risking instrument can take place, okay? So we need to consider the probability of putting it in place. And the second factor is its impact. So what will be the impact if we implement this strategy?
What do you mean, the first one?
Okay, for example, let's say if you consider before de-risking strategy, risking strategies, what are the risking factors? One possible risking factor is to have, let's say, a pandemic like Corona. Is the probability high to have a pandemic like Corona for the whole world? It's a very small probability. But if it will take place, its impact will be very strong. Okay? So we need to consider that this factor can take place or not, if it's risking or de-risking. Okay? So if it has a high chance to happen, we put a high score. If it has a low chance to happen, we put a low score. Okay? And then we evaluate the impact. So sometimes you can have very small probability of the event, but the impact will be really important. So this will higher the score of this measurement.
When you say probability of de-risking strategies, it's that their feasibility, how they're feasible as a strategy?
No, probability. Yes, exactly. So how much it's feasible, it's easy to implement or not. Okay, and for example, if you consider Lebanon, you know that one of the most barriers in Lebanon is corruption. It is easy to fight corruption. No, but if we can do it, it will have a very high impact. Okay, so of course this will depend also on the country where you are talking about. In some countries, corruption is easily confronted. Okay, so you say it's feasible to do it. We have a high probability of implementing this measure. While in other countries, it might not be. So depending on the situation, the country, the economical situation, the environmental effects, all of these can affect your measures. Okay? So For example, let us say we did statistics and we had the probability score for strategy 1 was 2. As usual, you put SK. You ask people, put a score from 1 to 5. If you have a high probability of this event to happen, put 5. Very low probability, put 1. And in between, put a score between 1 and 5. Okay, so let's say you got scores of 2. And for impact, for example, you got a score of 4. I will put any numbers here. So let's say 4 and 5, 3 and 3, and 1 and 2. Okay. Now, the total score for each strategy will be just obtained by multiplying the probability by the impact. Okay. So 2 times 4, 8, 4 times 5, 20, 3 times 3, 9, no, 4 times 5, okay, 1 times 2, 2. And now what is the next step? To normalize, because we need to get like weights, if you want, the weight of each de-risking strategy, okay? So if we consider, we just have now to compute the total. So 28 plus 11 equals, no? Yes, we need to normalize, exactly. So the total is equal to 39. So now we are ready to normalize. Whenever you normalize, you get the weight of each strategy. This means in percentage, how much it will contribute to de-risking compared to the other ones. Okay. So if I just do here, I should do 8 over 39 times 100. If I want to get it in percentage, I multiply by 100, or I can keep it as a fraction. 20 over 39, 9 over 39, and 2 over 30. Great. So now these are the weights of my de-risking strategies. But in general, how can I ask the question? Okay. You know, for example, whenever you apply de-risking strategies, okay, you can, for example, reduce, the discount rate. Higher the risk, the investor will tend to increase the discount rate or the rate of equity or rate of debit. So we said that the discount rate is a measure of a combination of equity percentage and debit. Okay, so let us consider, we need to see the effect of de-risking strategies on the discount rate. So in case you have a very risky project, the investor will put a very high standard to go through it. While if your project is more attractive, they can accept smaller value of discount rates. Okay, so let us consider, for example, that in this problem, in general, what do? We compare, if you want, the current situation. So let's say, for example, before de-risking measures, I can give you the value of, for example, the rate. Okay. So let us say it was around, let's say, 18%. So let us consider that the rate before implementing the de-risking measures was 18%. And after considering all of the strategies, what will happen for this rate? It will decrease because we'll reduce the risk of the project.